Thank you for joining our event tonight. I'm Jim Boyd. I'm the president of the MIT Club of Rochester, New York. Yeah, the mission of our club is to serve the local MIT alum community. We build connections, we foster networking, and we create events like the one we're going to present tonight that feature distinguished speakers on interesting topics. And, sometimes we recruit local speakers, sometimes we recruit speakers from the MIT campus, or from other clubs around the country and around the world. The other part of our mission is to uphold MIT's mission, right, which is to advance knowledge and to bring it to bear on the world's great challenges. And, so one of the challenges, one of the world's great challenges, of course, is associated with climate change. And that's been a theme of ours in many of our recent monthly programs. So we're going to start tonight by talking about a group at MIT called MACA, the MIT Alumni for Climate Action. And so I'm going to first introduce Jeremy Grace, who's the secretary of MACA, and he'll tell a little bit about the organization, and then he'll do further introductions. All right, Jeremy?
Thank you. If you remember nothing else from this slide, remember maca.earth. If you want to learn about MACA, go to maca.earth. We are MIT Alumni for Climate Action, and we appreciate this a chance to co-host with the clubs of Rochester and Western New York, and welcome you all. We're a nonpartisan group of MIT alumni and affiliates who are concerned about the devastating effects of climate change. We support communicating the urgency of the problem and adopting science-based interventions to drastically reduce the greenhouse gas emissions. We have a roadmap that you can read. It's a roadmap for addressing climate change. And that's on our website. And if you go to the next slide, we also have produced position papers on things like green alternative fuels and carbon dioxide removal to put some facts behind the hype and make some assessments about where these technologies fit, or are they fit. We have several different wings. We have advocacy and policy, which I head up. We have a campus group that works on decarbonizing the MIT campus, and is very active in that area. Advocacy and policy, we look at anything from local action to things at the federal and legislative level. We have an education group that is all about communicating the facts of climate change to the public. Entrepreneurship, about making businesses around addressing climate change. Climate justice, that group addresses what's going on a global scale and how the transformation has to be done justly. And then a technology group that gets into details about the various technologies to address climate change. We need more alumni, so sign up. Go to maca.earth/members and click on the red button. And thank you all for your attention. I will now turn it over to Robert Kars, the head of the MIT Club of Rochester.
Oh, yeah, I'm not head of the club, but that would be Jim Boyd.
Past head.
Okay.
Sorry.
First, I want to welcome everybody. Thank you very much. This has been a very, very popular topic, and because of that, you notice that you're all coming in muted, and please stay muted. We're going to our speaker will handle questions at the end, but we'd like to have the questions put in a chat. So please message me in chat or message everyone in chat if you have any questions. We plan on having plenty of time for questions after it's over. We will go as long as necessary for those. But again, please keep your speakers muted. We don't want to hear any dogs barking, things of that sort. Now it's my pleasure to introduce our speaker, who's Peter Vedder. He's Senior Director of the MethaneSAT Mission Systems at the Environmental Defense Fund. He's a Buffalo native, so he knows snow, but he's down in North Carolina right now. Ooh. He received his bachelor's degree in physics in 1982 from MIT and his PhD in astrophysics in 1988, also from MIT. He worked in industry, academia, and at NASA. Peter has more than 30 years of senior leadership experience in space systems and flight operations for a range of space science missions. For example, he oversaw development of deep space navigation for the UAE's Hope Mars mission and system engineering for a university-led Astrophysics CubeSat project. Since 2020, Peter has led the MethaneSAT mission and operation development. This includes ensuring operational readiness for launch and providing overall supervision of all aspects of mission operations. Following the launch in March 2024, Peter now manages the commissioning and long-term operation of the MethaneSAT. And I've seen a little bit of the talk. He's going to have some very interesting data for us. So, Peter, thanks for coming, and it's all yours.
Thank you for the kind introduction, Bob. And it's great to see the number of folks who are interested in this topic, and looking forward to hearing a lot of good questions towards the end. So let me get started and give you a quick overview of the MethaneSAT project and what it is we're doing and what some of the data looks like. But I wanted to start first with a quick look at the state of our planet. A number of you have probably seen this data in different forms. This is a measure of the average global daily temperature across our planet. And the heavy red line is from 2024. The lighter orange line is data from 2023. And then there's data from a number of decades below that. And a couple of things to take away if you haven't already heard. 2024 was officially the warmest year on record. In fact, the 10 hottest years on record have been the last 10 years. You can see the data below it. The dotted lines are 20-year running averages. And so those are slowly creeping up. But the planet is getting hotter. And in fact, it's quite likely that the coldest year you'll experience in the rest of your life was last year. Another way this is often presented is in this chart, which is sometimes called the temperature anomaly. It's basically the annual average temperature above the pre-industrial average levels. So in this case, they're using 1850 to 1900 as the baseline, showing the increase in global temperature above that point due to human activity. 2024 was the first year in which that peaked above 1.5 degrees C, which was the limit codified in the Paris Climate Accords. And even though 2024 was above the 1.5 degree limit, doesn't mean that we've broken the Paris Climate Accords in the sense that those are also use a running average over multiple years to determine when we've hit that tipping point. But it's not a good sign that temperatures continue to increase even above that 1.5 degree limit. Another interesting data point is the daily sea surface temperatures from plus and minus 60 degrees latitude across the globe. Again, the dark red from 2024, the orange from 2023, and you can see significant increases above the trends over the past number of years. And it's the sea surface which maintains heat, retains heat, and drives a lot of our daily weather patterns, resulting in things like this. In the upper left, the Los Angeles wildfires, which have been spreading over the past month. One of the reasons or one of the causes of those is believed to be hydroclimatic whiplash, meaning going between very hot or very wet and very dry years, creating vegetation, which then gets dried out and becomes fuel for wildfires. In the upper right, last June, Caribou, Maine set their hottest day on record when it felt like 103 degrees. In the lower right, Hurricane Milton, back in October, slammed into Tampa. It was one of the strongest hurricanes in the Gulf of Mexico. And in fact, it increased from a category 1 to category 5 in about a day, driven by the heat that had been built up in the Gulf of Mexico. And then the lower left, in my home state of North Carolina, Asheville received a ton of rain from Hurricane Helene back in September. For those who've never been to Asheville, it's well inland in the mountains and was often thought to be climate change proof. But in this case, the storm that came up from the Gulf retained enough moisture to dump it all over Asheville, flooding the rivers. They weren't prepared, and half of the town was basically destroyed. So what you're seeing is now reference to permanent changes to our weather patterns due to things like global warming. We're starting to see terms being thrown around like once-in-a-generation storms. You'll see news reports of once-in-a-100-year floods being referred to back-to-back years. So the climate is getting warmer. It's affecting our lives on a day-to-day basis. And studies over the past decades have attributed a lot of the climate change, a lot of the global warming to human-caused greenhouse gas emissions. There's been a lot of focus on carbon dioxide. That's an important greenhouse gas and one which we do need to continue to drive down. But another greenhouse gas which has received a lot of attention over the past decade or so is methane. And the main reason for that is methane has 80 times the warming power of carbon dioxide in the first 20 to 30 years after it's been released. If you look at the plots on the lower left, if you release 1 ton of methane and 28 tons of carbon dioxide at the same time, you can see the relative heat trapping capability of methane is several times greater than that of carbon dioxide over the first 20 to 30 years. Methane dissipates quickly in the atmosphere, and carbon dioxide stays as a more or less permanent constituent. So one way to think of this is carbon dioxide determines the total amount of global warming we see, while methane really determines the rate at which we're going to get there. So a lot of the near-term impacts we're going to start to experience can be attributed to the amount of methane we're emitting into the atmosphere. So where's methane coming from? These are data from the EPA's most recent survey of US greenhouse gas emissions with data from 2022. And roughly a third of the emissions are coming from oil and gas production, followed by livestock enteric emissions, landfills, manure management, coal mines, and then a little bit from wastewater and rice. Roughly 25 million metric tons were released into the atmosphere in 2022. That's the EPA estimate. But in reality, the EPA estimate is built on bottoms-up reporting from oil and gas companies, estimates based on the livestock counts, and estimates based on landfill surface areas. It's not based on actual measurements. But it's clear that oil and gas production is the largest source of human-caused methane emissions, both in the US as well as globally. So it really represents our best potential for near-term cost-effective reductions in this critical greenhouse gas. It's the low-hanging fruit. And that's why in 2018, Fred Krupp, who's the president of the Environmental Defense Fund, gave a TED Talk and said, let's launch a satellite to track a threatening greenhouse gas, methane. The goal of the project is to motivate and enable urgent action to reduce methane emissions, including cutting oil and gas emissions by 75% by the end of this decade. So that's really the mission, not just collecting data, but to use it to drive the reductions in methane over the next 5 to 6 years. Now, some of you may be asking why EDF, even who is EDF? The Environmental Defense Fund is a global nonprofit focused on stabilizing the climate, strengthening the ability of people and nature to thrive, and supporting people's health. We have a global presence based here in the US, but also in China, India, Indonesia, Europe, South America. And it was founded in 1976 after an avid bird watcher noticed a decline in the osprey flocks during the annual bird counts on Long Island. He consulted with a couple of friends. One was a professor at Stony Brook, another was a high school biology teacher. And after doing some research, they basically attributed the reduction in the osprey population to unhatched osprey eggs because of thin shells due to significant concentrations of DDT. Not content to do anything, they started the first GoFundMe called the Environmental Defense Fund to raise money to go off and sue to reduce the amount of DDT and stop the impacts on the local bird populations. And they were successful. And so that was the founding of EDF. And since then, our work has been guided by science, by economics, and working with both industry and government partners to find innovative solutions to environmental problems, such as methane. And that included some research in the early 2010s on methane in the US, which culminated in a study in 2019 called the Permian Methane Analysis Project, or Permian MAP, where working with some universities, commercial companies, we studied and measured in the field methane emissions from some relatively small areas of the Permian Basin in West Texas. That's an area familiar to those of you who may have watched Friday Night Lights or Landman, but those studies were done on the ground. They were done with trucks. They were done with some airborne flights. And the results at the end showed that the amount of methane being emitted, the amount measured by the different sensors being used, was roughly 3 times higher than what the EPA estimates were. And so that really motivated the need to find a way to get repetitive, global, high precision methane measurements to answer 3 key questions. Where is the methane coming from? How much is being emitted? And how does it change over time? In reality, it's hard to fly an aircraft over other countries, so it really can only be done from space. And so that was the motivation for the MethaneSAT project. It's been, as a satellite, specifically designed to deliver a new level of methane detection capability, which is currently not available. Equally important, all of the data we collect is going to be made public. We're looking to make sure that the emissions data we generate is transparent, how we developed it, how we analyzed it. All of our processing algorithms are all going to be made publicly available for free. And we're going to update it regularly so that everybody has access to the most up-to-date information on methane emissions across the planet. We designed it to have a very fine spatial resolution down to about 400 meters. That was important so we could help pinpoint where these emissions are coming from, not just give sort of a global estimate over a broad area, which really doesn't allow any action in terms of mitigating the sources of methane. The other thing we're doing, which is also different than other projects, is we are producing emission rates and fluxes for every single one of our observations. I'll talk a little bit more about that later and why it's important, but that's also something that's new and incredibly useful for those who are looking to reduce methane emissions. And so in reality, this is an operational mission. It's not a research project being led by an NGO, and it's been 100% philanthropically funded. So we're not a commercial mission. We don't have to make a profit. We don't have to sell our data. We're not a government-funded program. So we have flexibility to go off and collect the data that's most important to making a contribution to reducing methane emissions. Now, when EDF started this project, they had no clue how to build a satellite. So they started by recruiting a world-class advisory team to oversee the development of the mission. That included Tom Ingersoll in the middle, who founded 2 space companies, including Skybox Imaging, which was later sold to Google. Joe Rothenberg, who was the former director of the Goddard Space Flight Center and later NASA's director of human spaceflight. Charles Alachi, who was the head of the Jet Propulsion Lab for 15 years. Dan McLeese, who was the chief scientist at JPL. And Bill Preetz, who helped found some of the early Earth remote sensing companies like Digital Globe. With their expertise, they then recruited a number of key folks like myself to come in to help build the project, and also worked to get together the industry partners, the key industry folks that were going to be needed to build this kind of a program. And so that project team included companies like Ball Aerospace, who built our payload and did our flight system integration. They are now a part of BAE Systems, but Ball Aerospace is one of the premier space instrument companies in the world, if not the best in the world. They have built instrumentation for the Hubble Space Telescope, James Webb Space Telescope, and numerous NASA, NOAA, and Air Force satellite missions. We also have a partnership with Google. They're providing us with the cloud platform, which we use not only to fly our satellite, but also to do all of our data processing. And so we're able to use that platform, their tools, and their expertise in order to ensure we can make the data available to everybody as they need it. I'll give you a quick demonstration of that towards the end. The folks at Harvard University and the Smithsonian Astrophysical Observatory have been instrumental in leading the calibration and the data processing algorithms that we're using to process the data. They are some of the best in the world at doing atmospheric chemistry, and it's their some of their concepts that really formed the backbone of how we built the mission to be able to produce the data we can produce. And then lastly, early on, we signed an MOU with the government of New Zealand, and they're responsible for the day-to-day flight operations of the satellite. So the mission is actually controlled out of Rocket Lab in Auckland, New Zealand, and will be soon turned over to the University of Auckland. And they've also been providing us with the ground stations that we use to communicate with the spacecraft, and equally important, with the tracking collision avoidance services to make sure we don't impact any space debris. MethaneSAT is actually the flagship initial mission of the New Zealand Space Agency. And so for them, this is as important a mission as it is to us. One thing I'll point out too is that we started this mission in 2019, 2020, just as COVID was hitting. And from the start, we've done everything pretty much remotely. I've never had an office with EDF. I've done everything remotely, as have most of the team building the software and doing the operations. The only folks who really had to go into an office were the folks building the flight hardware at Ball and at Blue Canyon Technologies. But it's indicative of the kind of project that can be done today by remote teams with the tools we have. To put the mission into a little bit of context in terms of what it is we're trying to accomplish, there are other missions today, space missions, which can measure methane emissions in the atmosphere. They fall basically into two categories. The first are global mappers, missions like the European Space Agency's TRPOMI mission. These are missions which scan the globe with very, very wide swaths, very, very coarse resolution, in this case, 7-kilometer pixel scale. And they can see methane in the atmosphere, but really cannot pinpoint it as to where it's coming from. So it's kind of like your peripheral vision. You can sense there are things there. It's a bit fuzzy. You don't know all the details. So it's a good overall sense of the amount of methane, but really can't help you in identifying where to go look to try to reduce those emissions. On the other end of the scale are missions that do local mapping. Missions like GHGSat, which is a commercial Canadian company. These missions have very, very small fields of view, very high resolution, really designed to look at methane emissions where you know they're occurring to get a better idea. If there's something nearby that's outside their field of view, they won't see it. But they're very good at, as I said, once you know what you're looking for, if you want to monitor that specific point source, for example, after you've made a repair, this is the kind of mission that can do it. MethaneSAT was specifically designed to fill the gap in between, to marry the broader scale area-wide observations with higher resolution spatial and spectral resolution to be able to quantify the amount of methane emissions over relatively broad areas. So in this case, 200-kilometer wide areas with roughly 100 by 400 meter pixel scale. So MethaneSAT can actually measure emissions over an oil and gas basin like the Permian in 1 or 2 observations and collect that information and deliver it to users. Now, the spacecraft itself is 3-axis stabilized, so we're able to point it to any point on the Earth. It's got very, very high precision pointing, very low jitter, so we can get really good measurements on the ground. We have 2 state-of-the-art imaging spectrometers, some of the best in space at making methane measurements. As I mentioned previously, we look at about a 200 kilometer swath on the ground, and we point at specific targets rather than simply scan as we fly overhead. So each day we plan roughly 20 targets to look at, and I'll talk a little bit more about those in a few minutes. In terms of size, we're about 1.5 meters by a meter. Could fit comfortably on your dining room table, but on the other hand, at 380 kilograms, probably not something you want to put onto it. And thankfully, we have 2 fairly large solar arrays, so we have plenty of power to perform the mission. The 2 spectrometers both are identical, and we measure reflected sunlight off of the Earth, which comes in through our aperture baffle, through a slit, off a grating, and then onto our focal plane detector. Now, as the sunlight is coming back up to us from the ground, the infrared spectrum we're measuring has very distinct features for methane. The methane absorption bands are very unique. We can measure the intensity of those emission spectra and use that to derive how much methane is in the atmosphere. We have 2 different spectrometers, each looking at slightly different wavelength regions. One is focused on the oxygen spectrum from 1250 to 1300 nanometers. We basically use that to help us assess what does the atmosphere look like without methane. And then we have another spectrometer which covers 1600 to 1680 nanometers, which includes the methane spectrum, as well as part of the carbon dioxide spectrum. And you can see the spectral resolution of both is really, really high when we also oversample those spectra so we can get very good, precise measurements of the amount of absorption as we're measuring the methane quantity. And our signal to noise, as you can see, is close to 200 on the detectors. In terms of the sensors, I know there are a few folks on the call who are really into detectors and sensors. We are using 2K by 2K Mercad Telluride imagers. They're both identical in terms of their performance, in terms of their coverage. They're passively cooled. You can see the two copper straps are connected to a radiator panel, which we keep pointed towards deep space to cool the detectors down to about -85 degrees C. That keeps the dark count fairly low and gives us really high signal to noise in our measurements. Each imager, each detector actually is sort of subdivided into 8 separate 512 by 1024 regions, and we read out 8 of those individually at a frame rate of about 17.5 or 35 hertz. We normally operate at 17.5, but we can read them out faster should we want to for certain types of observations. We can also electronically select different subset regions, so we only select the key features in the spectrum to downlink because we don't want to downlink a ton of data that we don't use since we're bandwidth limited in terms of the amount of data we can downlink each day. And then lastly, the bezels that, if you look on the right-hand imager, that tapered black ring, which is the bezel holding down the chip. We cover several columns on the chip specifically in order to monitor the dark count. So we continuously monitor the dark count on every single frame that we read out. This is an image of the 2 spectrometers being integrated at Ball. You can see the 2 gold sets of detectors pointing up towards the ceiling are the entrance apertures and the objective assembly optics. And then towards the back in the circular housing are the two gratings. Another photo a little bit later on in the integration of the two spectrometers. Here you can see those two silver cylindrical cold fingers are what are attached to the radiator panel and eventually used to cool the two detectors down during operation. And then one last photo. This is of the completed spacecraft just before we shipped it to the launch site. You can see the two entrance baffle apertures there covered in the white thermal blanketing. In the upper center, the large gray panel is our X-band phased array antenna. Just to the right of that, sticking up is our S-band antenna we use for command and control. And then the silver panel to the bottom with the two different triangular sides is an earth shield. We use that to shield the radiator panel from any reflected sunlight off the earth to avoid heating it up. We take very careful steps to point that radiator panel at deep space to keep it as cool as possible to get the best performance as possible. So what does a MethaneSAT observation look like? As I said, we have a slit in the spectrometers. So when we look down at the ground, we're basically imaging the slit on the ground. And based on our orbiting altitude and the size of the slit, it covers about 200 kilometers wide and about 400 meters high. And then when you take the roughly 2K pixels across the slit, we get around a 130 by 400 meter pixel size on the ground that we're imaging. In the opposite direction, each of those dark gray pixels hits the grating and then is imaged on the detectors as a spectrum. So each individual pixel produces a complete spectrum in each of the two spectrometers. If we then were to add up those individual wavelengths, we could produce a grayscale image of the target. But it's that spectral information at each pixel which we use to derive the information on the global or the atmospheric constituents like methane. And we've aligned it so that the slit essentially, as we travel at 7 kilometers a second in orbit, in 30 seconds, that slit essentially sweeps across the target area. And as we read out the sensor at 17.5 hertz, we collect about a little over 500 frames of data. And each of those frames has the spectrum for each individual pixel across the slit. When you combine it with metadata on the instrument performance, things like temperatures, timing, all the transfer packaging, one target collection is roughly 5.25 gigabytes that we collect in about 30 seconds. Our orbit is a sun-synchronous orbit at 585 kilometers. A sun-synchronous orbit is a special kind of orbit in that the oblateness of the Earth, the bulge around the equator, causes our orbit to precess. But we precess at exactly the same rate as the Earth orbits the sun. And so what that means is every time we cross the equator going from north to south, we cross it at exactly the same time, 13:45 or 1:45 in the afternoon. We picked that time because that gives us the best lighting conditions to reflect sunlight off the ground and into the spectrometers for making our measurements. And so we get very consistent lighting from target to target, from month to month over every target we observe. We have 20 ground station contacts per day to 4 different sites. You can see there in those pink pins on the map in the upper right. And then downlinking it at 150 megabits per second, we get about 200 gigabytes of data per day. Thus far, we've downlinked a little over 5.5 terabytes of data from different targets we've collected since the mission began. I mentioned the MethaneSAT targets that we scan, 200 kilometers by 200 kilometers in size. We've built a target deck of roughly 400 targets that we pick and choose from every day in their mission planning. And we go through and we look at weather predictions. We look at which ones are visible from our orbit track that day. We also take into consideration which ones have a little bit better sun angle, because sometimes you're closer overhead, sometimes you're a little bit farther off to the right or the left. So we put all that into our algorithms to pick the best targets to observe each day, with an initial focus on oil and gas regions to meet the mission objectives. But we also have a large number of other targets that we've been observing, such as agriculture, landfills, wetlands, urban areas, coal mines. And so we not only are collecting data on oil and gas, we're also collecting data on a variety of other types of targets and how much methane they're emitting. We also do regular on-orbit calibrations. So we collect dark scans every day pointing to deep space to measure the dark current, so we can accurately remove that from each observation. We have a couple of LED lamps on each of the two spectrometers. We can use those once or twice per week to look at what does the sensor performance look like over time. Is it degrading in terms of its sensitivity? We can also use it to look for new dead pixels, which may have appeared due to a cosmic ray hit. We also take monthly lunar scans during the full moon, where we point essentially at a fixed location and let the moon sweep across our field of view as it orbits the Earth. And because the moon has a well-known albedo, and we know the solar spectrum quite well, we can use this to help with flat fielding as well as absolute response function of the imagers. Something else we do as part of our validation work is we observe targets which include a TCON, Total Carbon Column Observing Network site. What a TCON site is essentially MethaneSAT on the ground. So these are spectrometers which look up while we're looking down. So as we pass overhead, we can compare our measurement of methane to what they're measuring to do an intercomparison and validation to see if we're actually deriving with our algorithms the comparable amount of methane which they're observing from the ground. And then we further validate it by looking at some various controlled release sites where groups are releasing small amounts of methane of a known quantity. And as we fly overhead, we make measurements and then compare them to what was released and be able to use that to validate whether we're actually deriving similar amounts of methane as were released. So what happens once all this data hits the ground? First, we go through, we assemble it back into the image files. It comes down on a little over 2.5 million individual frames we have to reassemble. We correct for dark current, stray light. We do all the wavelength calibration, convert it to radians from digital numbers. And we also geolocate and georeference the data on the ground. So we use the onboard satellite GPS data, the attitude control sensors, which tell us where we're pointed on the Earth. And then we ray trace those against a digital elevation model to account for things like hillsides or mountains or valleys to make sure that where we geolocate the pixel on the ground is accurate. We then do the atmospheric analysis to derive the excess methane concentration. So we first remove clouds from any scenes that we see. We account for scattering in the atmosphere. We take surface reflectivity from existing land imaging to know roughly what we expect to get as an albedo. We also take into account absorption by different aerosols in the atmosphere. We use the oxygen channel as well as some of the CO2 data as a proxy for what the atmosphere looks like, what the meteorological conditions look like as during the time of our data collection. And the results of this is we're able to derive the methane concentration, the amount of methane in the atmosphere in terms of parts per billion in that specific area we observed. And then we regrid it into a latitude-longitude map of these methane concentrations in the atmosphere. Now, all satellites, including MethaneSAT, measure concentration. So what we measure is the amount of methane in a given column of atmosphere between the satellite and the ground. And we express that in terms of a fractional parts per billion. The challenge with using that is when you have wind or other issues, you don't know where that methane that you measured came from. So the amount of methane in the column you've measured could have come from outside. Some of the methane in the column could have blown out of the column at the time of the observation. So it becomes challenging to attribute the source, and equally important, how much methane was being emitted to produce the amount of concentration if you just look at a concentration map. And this is the kind of data which most satellites today distribute, because that's what they measure. But it's rates and fluxes which are the actionable information. And so that's what MethaneSAT is computing on every single target that we're observing. So we take the concentration data, we do inverse modeling of it, including all the appropriate real-time or as observed meteorological conditions like wind, rain, humidity, in order to derive the point sources, like a refinery, that were emitting a certain rate or quantity of methane to produce the observations we collected. For larger areas like landfills, we create a flux product, meaning the amount of methane being emitted over an area, roughly a square kilometer is the typical unit we use. But it's rates and fluxes that you can take and use and track to be able to determine where the emissions are coming from and how they're changing over time. So that's the last step in our data processing, where we compute those discrete point sources and the dispersed area emissions, and then we put them out into our data portal for people to use. Now, as we were building this data processing pipeline and working out the algorithms and developing the software to be able to do all this, we had a significant advantage prior to the launch of MethaneSAT. We had a platform called MethaneAir, where we flew a surrogate payload with a similar design and performance on aircraft to make measurements that we could use to verify and validate our data processing algorithms. We also flew the aircraft over some single blind controlled releases that were run by Stanford University to help us in understanding how accurately we could derive the actual methane emission rates from the data we were collecting. We had a couple of research flights in 21 and 22 on NSF Gulfstream 5 aircraft. And then in 2023, we had our own Learjet 35 that we flew these on for an extended period and collected a significant amount of data, which we were able to use in building up our data processing pipeline. We're planning to fly this aircraft again this coming summer over targets that we're observing with MethaneSAT, so we can continue to correlate the data and see how well we're doing between the two different platforms. A MethaneAir flight's a little different than MethaneSAT. We would fly it over the area. It would fly a raster pattern, kind of like a Zamboni, cleaning the ice. MethaneAir takes about 2 to 3 hours to collect the data. And during that time, wind and atmospheric conditions often change, which makes it a little bit more challenging to derive the actual results that we're looking for. And one of the things that makes MethaneSAT significantly easier is we observe roughly 4 times the area in 30 seconds. So the meteorological conditions, whatever the atmosphere is doing, really does not change significantly over a MethaneSAT observation like it does over an aircraft flight. I mentioned we performed some observations of a controlled release. This was designed so we could calibrate and validate our algorithms. And as you can see, we got pretty excellent results in terms of what we observed on the vertical axis versus what the Stanford controlled release amounts were. And these were a blind experiment, so we had no idea prior to submitting our results what the actual emissions were. And so as you can see, we got a very good correlation, which gives us very good confidence that the algorithms we're using, the techniques to derive the emissions rates are solid. We flew, as I said, a lot of flights in 2023 over a number of different oil and gas basins in the US. And we discovered a lot of methane, as you might expect. Significant amounts of methane emissions across 12 different large oil and gas basins in the US. And the real number to take a look at are the percentages on the color coding, which tell you the methane loss rate, meaning how much methane was being emitted as a fraction of the total gas production at that particular time. So in some cases in the yellow, 7 to 8% of the methane being produced was going straight into the atmosphere as opposed to into a pipeline. And you can see similar numbers in the range of 2, 3, 4% across all of the different oil and gas basins here in the US. In fact, the aggregate amount that we observed was 8 times higher than the 0.2 emissions intensity target, which 50 different oil and gas companies have signed up to. The aggregate that we observed was 7.5 metric tons, nearly 900 tons every hour, which is enough wasted gas to meet the energy needs of over half of the homes in the United States. Now, this is not, definitive. This is illustrative. The missions are going to vary over time, which is why we need something like MethaneSAT to continue the observations. But it's an example of what we're about to show you as the results from MethaneSAT continue to roll in, the kinds of things we can do with this data. So on March 4th of last year, along with 52 other satellites, we launched into space on a SpaceX Falcon 9 transporter mission. These are kind of like riding the bus into space as opposed to a taxi. You go up with a whole bunch of other spacecraft. And then about 2.5 hours after launch, we got dropped off into our orbital spot. And it was a huge relief to all of the folks who've been working hard on this project over the past 4 or 5 years. And so everybody was excited, but that's when the real work begins. So let me start walking you through some of the results we've gotten thus far. So this, just to give you an example, is the first light image we took, the first real image on the ground we took with MethaneSAT at the completion of our commissioning. So in this case, we've added up all the spectral information to create a grayscale image in the short wavelength infrared. And you can see that there's some agricultural fields down here, and up here you can see features on the ground. You can also see where there's clouds, as well as the shadows being cast by those clouds. We were intrigued by the very bright emission, or very bright object we saw there in the sort of the middle area. And when we zoomed in, it looks like that's a solar array farm that's roughly about 7.5 kilometers wide. And then if you look at what is the spectral performance, these are single pixels, so only a single row of the imagers from both the methane and the oxygen sensors. And everything you see in that is real. The noise level is significantly lower, so we have a very, very rich spectra, a large amount of information we can use to calculate what the atmosphere is doing and how much methane we're actually seeing in the atmosphere at any one given time. So here's another image of the Permian Basin. This is one of those concentration maps, the data we actually obtained with the mission. And I wanted to show this to you to point out 2 different things. Now, first, you can see kind of the yellowish areas. That's the methane, higher concentrations of methane. And you can get a sense of the wind blowing the methane, kind of like plumes of smoke. The other thing I'll point out on the right-hand side are the holes. Those are where we removed clouds from the data that we first got down. And one of the advantages we have with MethaneSAT is our high spatial resolution allows us to actually see between clouds and around clouds. We can actually get data and information in between those clouds that we can use. Other missions would take roughly the right third or half of this image and throw it out because of cloud cover. It would be unusable given their resolution. That comes in handy in areas like Venezuela, which is notoriously cloudy. This is an oil and gas basin in Venezuela, and you can see a lot of the holes where we removed clouds but you can also see the methane measurements we're making around those clouds and able to actually derive fairly high amounts of methane emission. These are the kind of data which other satellites have not yet been able to produce and really give us some of the first quantitative information in the Venezuelan basin as to how much methane is being emitted. So this is the kind of data that we're starting to produce and put out. This is a map of the Permian Basin from last September. The green dots are point or discrete sources, and you can see on the scale on the right-hand side how much methane is being emitted in kilograms per hour. So the largest is roughly 13 tons an hour. And then the heat map represents area emissions. And so what these are really unresolved emissions which are too small for even MethaneSAT to resolve, but which in aggregate contribute a substantial amount of methane emissions. So you can see in the bright yellow areas down here in the left-hand corner, we're seeing emissions and measuring emissions of order 400 kilograms per hour per square kilometer. And so over this entire area, we see about 253 tons per hour. And in this particular image covered 90% of the Permian Basin production. The Uinta Basin in Utah, we didn't see any point sources, but again, a lot of small independent individual sources which combined produce a substantial amount of methane. This is data we collected over Appalachia on the Pennsylvania-West Virginia border. Here we saw a number of different point sources of different types. So the green circle is an oil and gas facility. The darker blue are landfills. You can see they're emitting quite a bit of methane. And then the lighter blue are a number of coal mines that are emitting methane down near the West Virginia border. And you can see also the bright yellow region is likely a fair number of coal mines emitting small amounts of methane, which in aggregate produce a substantial amount of emissions. In Turkmenistan, the Amu Darya Basin is one of the largest producers, also one of the dirtiest. Here we're getting about 120 tons per hour of methane being emitted. Also in Turkmenistan, they have a facility near the Caspian Sea. This shows a number of individual point sources with quite high emissions, and the total area is a whopping 420 tons per hour of methane being emitted. Now, if you look at what those emissions are compared to the estimates, remember at the beginning I mentioned the EPA reports are based on their estimates, which are bottoms-up estimates. They will take, for example, from an oil and gas production facility, the number of valves, what it's expected to leak at, etc., and add those up. We're actually measuring 3 to 8 times more emissions from every single basin that we've looked at thus far compared to what the bottoms-up estimates are. So the amount of methane that's being pumped into the atmosphere, a lot of the modeling is based on the estimates from EPA and other sources, but the real quantities are significantly higher. The other key finding that we found thus far in the limited data we've looked at is that up to 75% of all the methane emissions that we're seeing are coming from these aggregated, small, dispersed sources, not from the individual point sources. People tend to focus on the big point source emitters, and yes, it's important to shut those down, but it's the things like on the right-hand side, which were observations made in a Romanian oil and gas field, where you have rusting valves or gaskets which have not been maintained, which are just leaking continuously small amounts of methane into the atmosphere. But when you start adding that up over a huge oil and gas field and a lot of this equipment, it produces a substantial amount of the emissions we're measuring. One of the challenges we have thus far, and we need to continue to work at, is attribution. So this is an example of data we took over the Permian Basin where we saw emissions where that star is in the middle. But if you take a look at all of the oil and gas infrastructure that's there, every green dot is an oil or gas well. The gray lines are pipelines or other facilities. So when you try to attribute the emissions to a particular source, it becomes harder. We have sort of a 400 or 500 meter uncertainty on our positions. And if you look at the bottom scale, you can shift that star around a little bit and hit just about anything near the center of this picture and attribute it to that. So attribution becomes a challenge. And what you'll see on our website is we're leaving that up to the user to evaluate. We're providing the information, but we're not specifically naming a specific well or pipeline as the true source of the emissions. Now, oil and gas are important emitters. I just wanted to show this as an example from data collected both during Methane Air and MethaneSAT. This is a coal mine in West Findlay, Pennsylvania, where we've seen emissions consistently over the course of a year between 3 tons and 1 ton of between 3 tons and 1 ton of methane per hour. And so this is the kind of power of having a satellite being able to make repeated measurements of a target and monitor how much emission is coming. Are they making improvements? Have they been able to cut down on some of their emissions, or are they continuing at the same pace or increasing? So all of this data is available to the public for free on our website, data.methanesat.org. I'd encourage you to go take a look, where you'll see data like I was just showing you, in this case, over the Permian Basin. And as you zoom in, you'll see that image I was showing you earlier, where you can look at individual point sources, how much is being emitted, where they're located, and what facilities are nearby. As you zoom in closer, you can see the oil and gas, or the area emissions heat map. And as you continue to zoom in, you'll eventually get to the oil and gas infrastructure database, where you can click on individual wells or pipelines to see who owns those and which might be contributing to the methane emissions that we're seeing. All that data is going to start to become available. We put the initial data out on this portal. It's available to download through the Google Earth Engine, so you can actually download it and use it. And then we also have data from our methane air flights in 2023, 2022, and 2021 available. So I'd encourage everybody to go take a look, start poking around, start exploring the data, and we're going to continue to add more and more of it as we put it through our data processing pipeline. Now, the data that MethaneSAT's collecting is important, but it's not a silver bullet. It can't reduce methane emissions by itself. It really requires folks on the ground, whether they're in regulatory agencies, whether they're in oil and gas companies, or whether it's just a local citizen like yourselves who's getting involved and looking to try to find ways to reduce methane in your neighborhood, in your state, or in your region. And so that's really what's required to make use of the data we're producing, to go off, to talk to government officials, talk to local companies, talk to your local state and local governments, and use the information we're providing to continue to drive down the emissions of methane. So with that, appreciate it. Look forward to a lot of good questions. Thank you.
Okay, very good. Thank you very much, Peter. Very, very, very informative, and as indicated, basically everybody who signed in here stayed the whole time. So that's very good. We got a ton of questions here. I think that first, everybody just explain to people. We did. I gave everybody a thumbs up, indicating that I read the question and that you were kind of on the list. That'll be addressed in some way or another. And I just want to go to a couple of quick questions that aren't directly for you, but are directly. Well, one of them is directly for you. Will there be slides available afterwards? These are just quick questions. Can we make the slide package available?
Yep, we can make it available. Mm-hmm.
Great. Okay. And let's see. And the rest of them were, okay, that was the only general question. So now let's get to the specific questions. I think we'll start out with the one that we asked you for originally, which was from Jeremy Grace. Do you know of any companies, groups, or governments who have already taken action based on the data from the MethaneSAT data as reported to date? Has anybody taken action yet? you know?
Yes, so there's a couple things happening. Number one is EDF, who are the original motivators for the MethaneSAT project. We've been working with several oil and gas companies, Shell and BP primarily, and so they're interested to get the data. They're interested to understand their own methane emissions so that they can go and make the appropriate adjustments in their oil and gas fields to make those reductions. So we've been working with them already. The other is the UN Environmental Program, UNEP, has the International Methane Emissions Observatory, which is intended to be a global clearinghouse for all data related to methane emissions. So we've been contributing our data. We've been actually been working with them on their data portal to deliver our data to them. And that's also being used by a number of government agencies to start looking at further regulations on methane emissions.
Okay, very good. And the question, and what do you think the prospects are for U.S. and international government groups taking meaningful action based on the data? In other words, is there any enforcement here? You know, I mean, are people cooperating, or can we force them?
Well, as I said towards the end, it really comes down to the people on the ground. We're making the data available. We're working with different government agencies, different commercial entities to try to encourage them to take the data and the information and make meaningful reductions. There are different regulations across the globe where our data is being used. For example, in Europe, they have some strict regulatory requirements when you're purchasing gas products from an overseas entity, that it comes from a facility or comes from a production field which meets certain emission thresholds. So if you're dirtier than that, they're not supposed to purchase that gas or oil. And so they're already beginning to use our data as a means to evaluate, are we buying data from a clean source or a dirty source? So in some respects, the marketplace will start to drive some of those reactions, because other countries have already set some regulations as to the kinds of a product they're willing to accept.
Okay. And another area, Kimberly Lynn Drake asked this question. If livestock is so close behind oil and gas production in the percent of total methane released, then isn't moving to plant-based diets an equally low-hanging fruit to reducing oil and gas emissions?
Potentially. It depends on the energy that's required and where that energy comes from to move to a plant-based, diet. That's one of the things I will say that EDF is quite good at doing, is not just simply saying we have to cut methane emissions so we get rid of livestock, but what happens when we switch to an alternative? So, for example, when you look at industrialized agriculture, where you start to build facilities to do agriculture at a larger scale, they're going to consume energy, electricity, whatever, and that has to be produced somewhere. So what is the net impact in terms of methane emissions from that? There are, in fact, also organizations who are looking at ways with some different drugs to try to reduce the amount of methane emissions from livestock. So there are different alternatives being evaluated to try to reduce livestock emissions as well.
When will Hampton Watkins asked this question? When will data from decomposing methane chlorate above 55 north become available? Specifically need to understand the Arctic contribution from tundra release to the total.
Yep. That is one of the things that's on our list to start looking at. One of the challenges we ran into was we launched in March. We did our engineering checkout, started collecting our data, and then started going into the fall when the lighting conditions in the far north become less favorable. We expect come summertime, we're going to start taking a lot more images of different target areas in the far north, both in Siberia for some of the Russian oil and gas fields, as well as some of the permafrost, which is melting, to measure some of the methane emissions there. So we have to kind of wait to get the right lighting conditions. It's a bit dark up there right now.
Got it. Dr. Jim Conroy just made the point that sometimes human behavior is hard to change. Can we get people away from things that use so much methane? But there wasn't really too much a question there. Let's see. A question from Neil Dale. Let's see that the main emissions of cattle operations come from large factory operations, large pools of excrement, and high methane burps from grain-fed cows. Properly managed grain-fed cattle can actually participate in long-range ecosystems health. Okay, that was more a comment than a question. Okay, I think you sort of answered this, but do clouds interfere with MethaneSAT? And I guess they do.
Mhm.
But does smog?
It can. We can actually, we actually made some measurements through smoke from wildfires during the wildfires in 2023. So we can actually see through some of that.
Okay. This is a pretty good question, Jack. Sleebeck, everyone. How much do methane emissions change throughout the day? Is it possible for emitters to hide emissions by avoiding observation times? Here comes the satellite, turn it off.
They can. Yep. And we expect that will happen in certain situations because we're in a predictable orbit. They can tell when we're flying overhead. So there are activities such as pipeline maintenance where they blow out a lot of the gas in the pipeline if they're doing some maintenance or cleaning it. And so if they chose, they can do that after we've flown overhead. That's really nefarious, and we'll see if any of that happens, but there's no way we can avoid it or check on that.
Is it possible? Catherine Gorham asked this one. Is it possible to obtain meaningful retrieval over ocean or reflective ocean surfaces? Can you get data over the ocean?
Yes. So one thing I didn't really talk about was that right now we are looking pretty much straight down at targets. And when you go over water, it tends to absorb the infrared better than reflect it. But there's ways that we can measure offshore oil platforms with something called glint mode, where we look at an angle with the sun essentially bouncing off of the water and then up to the satellite. We haven't yet implemented that. It's in our roadmap to add that in. And with that, we'll be able to observe offshore platforms and other contributors off the coastlines once we add that capability.
Okay, very good. Dan Nolet asks, has revised data been included in the En-ROADS model, the MIT Climate Interactive Map?
I do not know
what he means by that.
Question.
Okay.
The data is available, so if there's interest in using it, please feel free to head to our portal or contact us.
John Randall wants to know about what incentives emitters have to fix leaks. I think that you've been over that, though. I think that's been largely answered. Here, Mike Carmenzind, sorry for the names here. I'm not so good at this. Carmenzind, Mark Carmenzind. For hotspots, can surface low-cost land-based detector arrays be used, combined with wind direction and velocities to find point sources?
They can, and many oil and gas facilities do deploy their own measurement devices across their production facilities. Unfortunately, again, it depends on the wind direction. It depends on what the emission is, and typically, if they're far away, they can't see the smaller leaks. So yes, they can do that. That's part of what was used during the Permian map ground-based study in 2019, were some of those exact same sensors.
Okay, I'm trying to make sense of this one. Could data be used to, quote, black eco-mail, I guess, eco-mail government corps, or even individuals, or at least influence them? In other words, blackmail, is that what we're talking about here? I'm not sure.
Those are the kinds of things, as I said earlier, we leave to others. We're making the data available. We're not specifically going to turn into the policeman and try to do anything of that nature. But as I said, the data is available for organizations to try to do whatever they choose in terms of reducing methane emissions.
Any data from California yet? I was kind of surprised about that too. I don't think we saw too much from it on the maps.
We haven't looked at much data from California. We did with Methane Air, looked at some of the San Joaquin Valley, but we haven't yet looked at it with, actually, I take it back. We have looked at it with MethaneSAT. We just haven't put it on the data portal yet.
Okay, because that was what they had a big leak there a couple of years ago, enough to poison people. So
They did. They did. Yeah.
okay.
One thing I will say is what the data I showed you is only the tip of the iceberg. We have roughly 700 other targets that we've collected and are in various stages of processing. We've been very methodical. We want to make sure that the analysis we're doing is accurate. We've had a number of independent scientists checking it to make sure that it looks good, because we don't want to put out information which somebody can point to as erroneous, which then just erodes the trust in the future data we put out. So there will be a plethora of data coming out to the website pretty soon.
Okay. We've had a couple of questions, a number of questions kind of repeated, so maybe we'll just touch on it. That 40% of the methane budget is attributed to aquatic sources. You already said that you can measure them. And I assume we do see some natural emissions from the ocean. That was the question. See any natural emission out of the ocean? Must be at least a small amount of it.
There's a small amount, and as I said, once we improve our glit mode operations, we'll be able to measure those.
Okay. Is there any way for scientists, this is from Jason Silbeck, is there any way for citizen scientists to request specific geographic areas for mapping?
Certainly, we're welcome to folks contacting us if they have specific targets. We have a very detailed process, obviously, to put targets into our target list and select them. But if there's specific targets that are of interest, we're always open to hearing what those might be if there's something we're not aware of. Okay.
This is an interesting question given the current political agenda. Do we have alternative, Dan Granberry asked this one, Darnell Granberry. Do we have alternative channels in mind in case Google, and thus its products, are pressured or co-opted by our anti-science administration? A little bit loaded, but.
Yeah, no, that's something we have been thinking about, is what do we do to either move our platform elsewhere or pay Google if they're no longer willing to contribute. But we have been looking at different options should different situations in the current administration play out.
Okay. From Carlos Rigatui. Oh, sorry about the names, everybody. Trying. Is it possible to subscribe to data rather than downloading it from your site?
We're in the process of building that into the data portal. There's a couple different features we're planning to add over the course of time. One would be kind of a subscription or an update. We also are making some of the raw data available to scientists and academic institutions to download the full raw data as well. So that's something to stay tuned for.
Okay. Neil Dale asks, has measurement from tropical wetlands been measured? Is it rising? And approximately how much of the total increase have wetlands become?
We've made some measurements of wetlands. We're still going through the analysis of what those mean in terms of, are they increasing? Are they decreasing? Are they staying the same? But we have some early data on that. It's not yet ready for a public release, but it should be coming up in the not too distant future.
Vanessa Glavinskas asks, will the MethaneSAT show methane emissions from melting permafrost? If it does, that would be a worry that massive amounts of methanes are being released by melting in the Arctic, right?
Yep. Now we can measure it if it's substantial enough, and given the sensitivity we have, we do expect we can measure some of the melting permafrost and be able to quantify the amount of methane. And yes, that's worrying. What I will say, though, is our primary focus is on making measurements where we can make a difference and try to ratchet those down. Something like melting permafrost, there's very little we can do other than monitor it. So our primary focus and targeting has been on things like oil and gas, where we know we can go off and try to make reductions.
Okay. Jasmine Sinkular asks, are there a lot of as there is a lot of stonewalling as to the meaning of data, Is there a way to tie the atmospheric and sea level temperatures with the methane emissions in real time to show the significance of this data?
It depends on what you mean by real time. Certainly, you can show correlations between them. It's hard to do anything in real time in terms of the measurements we're making because it takes usually several days to do the processing. Similar with the global temperatures, it usually takes a couple of days for those to be processed and published by things like the European Climate Center. So you can certainly draw those conclusions from the data that are being presented in a couple of different fora and put those together to get those, to drive those kinds of conclusions as opposed to more real time.
A couple of questions. I say skeptics. I wanted to get one. We had a lot from the center's iPhone, but this one question I want to put out there. Why do you feel you have a smoking gun when methane in the column can come from any source mixing over time? And
that's
I don't
why
think
we
you claimed it.
Right. That's exactly why we do the inversion, where we do the modeling to assess where the potential sources are for the methane in the column. And so the advantage with MethaneSAT is we're taking essentially a snapshot. It's not a movie where things could mix over time over a long period. Instead, it's a pretty instantaneous picture of the methane in the column. It's basically static. And we can then look to modeling with the different inflow patterns from the wind, from the meteorology, from the atmospheric conditions, the boundary layer. We can then use that to model and invert to determine where the sources of methane would be in the column we observed.
Okay. And then, well, this one I don't understand. I'll just put it out there. Is there a better place to start to look at treatments for livestock? I don't know about better place, but you already just mentioned a couple. I think we can skip that for time. Mark Timedzed again asks, he said, I love low cost land-based purpleair.com particle maps for the world, and anyone can look at any time. Hope low-cost methane sensors can be used in this way. I guess you sort of are doing it. Okay. Okay, let's see. Would it be possible to get Jonathan Perry asks, would it be possible to get higher resolution data with smaller area by maybe taking overlapping measurements?
Yes, that's one of the reasons we have the higher data rate, the 35 hertz readout rate. So what we can do there is we can actually, instead of moving the slit at the spacecraft orbital rate, 7 kilometers, by adjusting the way we observe and by basically turning the spacecraft as we fly over, we can get slightly higher resolution, higher spatial resolution, as well as higher sensitivity data. That's not a mode we've yet exercised. It's in our plan to do that over certain targets, but we do have that capability to do it.
You're just getting to know it. How long does it take for data to capture the data? How long does it take from data capture to publish? What is the target latency in the future? What's your latency?
So the target latency is on the order of 4 to 5 days. There are certain factors which drive that. Number one is we collect the data and doesn't necessarily come down right away. It could take up to a day before the data gets downlinked from the spacecraft. We then have to wait for the observed weather information. So we use the observed wind speeds, atmospheric conditions, temperatures, pressures over a given target area as part of our analysis. Those are often not available for a day or two. And so once we get all that, it takes us about a day, day and a half to process. So the target latency, when you also include a quality check in there, is to get it available within about 4 or 5 days after the observation.
Okay. This question I had. Can more methane satellites be added for higher coverage? Or more specifically, what is the approximate cost for an added satellite? And what's the approximate cost to run a satellite for a year? Those two are I was wondering about.
Yep. So MethaneSAT was built for just under $100 million, which is significantly cheaper than a similar NASA spacecraft. In fact, we've been meeting with NASA. They are eager to learn how we can build a mission of this quality so cheaply. So we've been in conversations about, building more spacecraft, and obviously there's NRE that will no longer be required, so we can build a copy a little bit cheaper than 100 million. And it takes around $4 to $5 million a year to operate the mission. So it's relatively cost effective in terms of the return of what we're getting from the data. And there's a significant number of philanthropic foundations that are eager to fund these kinds of projects.
Where are you getting your funding? Most of the funding, is it all just private, small contributions, or do you have a couple of big donors? Or
all of it is philanthropic. A lot of it is from large foundations. We got a fairly large grant from the Bezos Earth Fund, about $100 million. There's a few others, the King Foundation, the Heising Simon Foundation. There are approximately 40 different organizations which contributed to the MethaneSAT project.
Okay, well, this one I don't understand. Well, let's try it. What percentage of the GHGs are methane, and did your data result in any revision? What's GHG?
Greenhouse gas.
Okay.
So the answer is it's about, I saw the number, I'm trying to remember. I think it's around 10 or 12% of the greenhouse gas emissions are methane, or believed to be methane. But the answer is yes, we can quantify what we're seeing versus what the estimated amount of methane that's believed to be emitted, and help to adjust that as part of that equation. So what's the total amount being emitted in reality versus what the estimated amount is? And so that can help with that overall percentage.
Okay. I thought I asked another question, then he sort of answered it. So this seems to be like trying to track the sources of pollution to a specific car or measured in a column of air from miles away. Needle in a haystack accuracy would be questionable. But then he says, so the inversion modeling using weather data is key. Yes, it is.
It is.
Also, I'd say that most of your sources are stationary, not cars. Yeah. And he asked about the Chinese deep sink. Have you heard anything about that? I'm not sure.
The new AI tool? Is he referring to the new Chinese AI tool? DeepSync?
I don't think so. Well, maybe he is. Yeah, that's what he is. Yeah, that's what it is. DeepSync. Okay. Do we have the Jonathan Perry asked, and we're getting near the end of the questions here. Do we think it's feasible to collect this resolution data for the entire planet, or would it be limited to specific targets? Sort of.
We could collect it with enough time and enough spacecraft over the entire planet. The real question is the benefit to observing certain areas where there's likely to be very little, if any, methane emissions. So that's why we've focused in building up our target list to areas where we believe we're going to see significant methane emissions.
Okay. And this is a good question from Tim Johnson. What's the market value of the leaked methane emissions? What do we think it is?
Quite a lot.
It's a lot.
It's a lot. And that is exactly why a lot of companies like Shell and BP are interested in talking to us, because it's revenue going into the air that they want to track down and fix. They want to fix some of these leaks, particularly the larger ones, because they're losing gas that they should be selling to customers.
Yeah, that's very important. The final one is not a question, but an interesting comment. You might be interested. You might want to follow. This is from John Randall. No, not John Randall. It's probably says though. I prefer to see hotspots on your diagrams in bright red, not green. Well, that's good point. Maybe
I will. Yes, and I'll make a comment to that. In that we EDF actually has a team of social scientists who we engage when we are building things like those maps in order to understand how people are going to receive them. And we go through a lengthy process because one of the things EDF has learned over the years is you have to be good at communicating the information to get any kind of action. And so the colors we picked were after a lengthy analysis. There was a number of focus groups that looked at the data in different color palettes to find the ones that they were able to most understand the information. And while red may have come across as something which was alarming, a large amount of methane, they settled on green for some reason. I can't remember the exact reason, but it was our social science team which made that decision.
One final kind of question that I skipped over. I must have missed it because I remember seeing it. How frequently does a given spot on the Earth get measured?
It depends where it's located. And so closer to the poles, we can see it much more frequently. Near the equator, less frequently. But when we pass over a target or we pass near a target, we can usually see it for 3 or 4 days in a row. And then we have to wait another 4 to 5 days, and then we come back around again and can see it for another 3 or 4 days. So we can visit targets fairly frequently.
Okay, very good. That's the end of the questions I got from Larry Petro, and I want to agree with everybody on this one. Great talk, Peter, and great mission. And I wholeheartedly agree with that. And I'd say also, just for your information, most of the people that joined are still here with the questions. So it shows you it's a very pertinent topic. A lot of people interested. So thank you very much. Thumbs up.